Hello everyone. In this video we are going to look at one of the I would say a little bit more difficult topics in nonlinear control called sliding mode. So what is a sliding mode control? So to explain that to you, let's look at a single input single output system given by this relation that nth derivative of the output is equal to some nonlinear function of x plus another nonlinear function times u, okay? F and b are known functions, but they have uncertainties in them. And the vector x here is the output plus what? Plus all of the derivatives of the output. Good? Now, as I said, f and b are known functions, but they have uncertainties, and these uncertainties are bounded. For instance, like in a physical system, a mechanical system, let's say, friction is never exactly perfectly modeled, or inertia. They are only known to some level of accuracy. So we can have some bounds on the values for friction coefficients or inertia, but not know them perfectly well, especially friction. Good? Also, if we want to achieve perfect tracking, which basically means making x to go to x desired, we set the initial condition for the states to be the same as the desired ones. So we right away can make x converge to xd. If initial condition of x and xd are different, then it takes a little bit time before x converges to xd. So here we assume that the condition for x of 0 is the same as xd of 0. As I said, if not, I'll show you what happens. But here we can have this assumption. So the goal is to pick this u such that x converges to x desired, although there are uncertainties and although the system is nonlinear, right? And here we don't want to do adaptive control. We want to do basically sliding mode control, which is basically a category of robust control. So we want to make sure that despite these basically disturbances in the system, which are due to unmodeled dynamics, the parts that we didn't model or we simplified, or the variation in parameters, we still able to achieve tracking within so much of accuracy, although it might not be super perfect, but still the system performs the job. So if we define the tracking error x tilde to be x minus x desired, we define here a surface in the state space through a scalar function s of x and t equals 0, where the operator s of x and t is equal to d over dt, the time derivative operator, plus lambda, a positive constant, raised to the power n minus 1 times x tilde. So basically a polynomial of derivatives and constants times what? Times the error in the output x tilde. This x tilde is different than this one. This one is just for the output itself. This one with bold font means all of them, all of the states variables. For instance, if n is equal to 2, and n here is the order of the system. So if system is second order, n is 2. If the system is the third order, n is 3, and so on. So for instance, if n is 2, a second order system, then s is going to be d over dt plus lambda to the 1 times x tilde. If you multiply, you get d over dt of x tilde, which is x tilde dot, plus lambda times x tilde. Or if the system is third order, then you get d plus dt plus lambda squared, and clearly this guy is going to be d over dt squared, correct? Plus 2 times lambda times d over dt plus lambda squared. If you multiply it by x tilde, then you get x tilde double dot plus 2 lambda x tilde dot plus lambda squared x tilde. Correct? Good. So why we call it a surface, I'll show you. But here we define this, and if you look at my previous videos, you see that this is basically the same as that combined error, especially for a second order system, right? You see that for a second order system, remember that was E dot plus lambda times E. This is the similar idea. So now what do we do? Now, if initial condition 2 is satisfied, which means the system starts at the same initial condition as the desired one, the problem of tracking, which is forcing x to converge to x tilde, now is going to be equivalent to what? To making the trajectory of the system in the state space to stay on the surface S. Okay? Why is that? Let me show you. Why? Because if I force the system to stay on the surface S of x and t equals 0, that means d plus dt plus lambda, d over dt plus lambda to the n minus 1 times x tilde, this whole thing is equal to 0, right? So now you have basically an ODE, an error dynamics. So not only this S of x and t equals 0 is actually the equation of a surface, it is also, as you can see here, this is also your error dynamics equation. So this surface is what? This is the surface of your error dynamics equation, this S. And if you can stay on this, okay, then clearly if this operator times x tilde is equal to 0, this operator cannot be 0 all the time. The only solution is x tilde is 0. And when x tilde is 0, that means x is the same as xt. Good? Now, as I said, we call it a surface, huh? So what does that mean? Well, let's look at a simple case of a 2D system, which is this one here, where S is x tilde dot plus lambda x tilde, okay? So if we set S to be equal to 0, let me write it. What does it mean in the state space? And in this system, the state space is what? Of course, x and x dot, correct? Because it's a second order system. So what is this? This is x dot minus x desired dot. This is x minus x desired. Okay, now what would you get from here? You get that x dot is equal to what? Xt dot minus, if you take it to the other side, it's going to be plus lambda times this xt term, and then you're going to also have a negative lambda times x. So let's write that one as well. And if this is a constant or a variable term, right, it could be a function of time or constant. Clearly, you see this is a relation between what? X dot and x. So in this case, it is going to be a curve, right? And again, if this lambda is constant and these are constant too, it could be, for instance, a line. Now, if the model is more complicated, so n is 3 then, right? Then you're going to have x, x dot, and x double dot, right? So you're going to have something like this. Your state space is now going to be three-dimensional, and it is going to give you a relation between x, x dot, and x double dot. And in that case, now you're going to have a what? You're going to have a surface. Okay, so in general, this is a relation between all the state variables, and it is a surface or a hypersurface in n dimension, and clearly a single line in 2 dimension. Okay, that's why we call this S of x and t equals 0, we call it a surface. Good. And as I said, the problem of tracking is staying on the surface, because on the surface where S equals 0, the only solution is that x tilde should be 0. And that means your x and x desired should be the same. So as long as you can have the trajectory of the system to stay on this surface, that means you have the system under control. The problem is when you start in the beginning, you might not start right on the surface, you might start here. So now if you pick your control signal U such that you can control the trajectory of the system so it is getting attracted to this line, right, from wherever you start. So whether you start here or here, if you can get all these trajectories to get attracted to this line or this surface in general, then what does it mean? So let's say here, if I start above it and then I can come and fall onto it, right, then I can guarantee convergence of tracking error to 0. And since the you can see that the trajectory is moving on the surface, we call it what? We call it sliding. It's like your state space particle, your location in the state space is literally sliding down the surface. Okay, so we call it what? We call it sliding mode control, and the surface S, we call it the sliding surface, as I have shown down here, and I have mentioned to you that basically the surface is called sliding surface, okay, and this control is called sliding mode. There is a couple of other terminologies that I need to tell you about it. So that's one thing. The other thing we need to talk about is not only if you are on the surface x tilde is 0, but also if your initial value of the system, if you picked x initial 0 such that your initially the distance you have from the surface is, so this s acts as an operator on the surface is exactly 0, and then above and below it could be positive or negative, right? So you might have something like this. On this surface or on this line, s is equal to 0, and then let's say on this side of it, for instance, s could be positive, on this side of it, s could be what? Negative, because it acts like an operator. So as long as your distance to the surface is within, initially, if it's within some parameter phi, then you can show that the ith derivative of x tilde, the magnitude of that is also going to be less than or equal to lambda to the I times epsilon, where epsilon is that distance phi over lambda to the n minus 1. Again, n is the order of the system. Lambda is this parameter that you choose in the surface, right? And it can clearly change the orientation of the surface, right? And I is the order of the derivative. For instance, for that second order system, if equals 0, so we have I equals 0, then that's the 0th order derivative, which is the x tilde itself. So you'll see that the magnitude of x tilde is going to be basically 2 lambda to the 0, 1, which is going to be less than epsilon, and epsilon here is equal to phi to the lambda to the 1, because n is 2. And that is understandable if you look at, for instance, here, this, what you can see here is the diagram of the relation between s and x tilde. So look how you get s from x tilde. S is derived from x tilde by applying this derivative operator plus lambda to the n minus 1, right? So this is like d over dt plus lambda, which is multiplied by itself n minus 1 times, correct? And the question is, here you apply all of this on x tilde, and that gives you s. So on the other hand, if I give you s and I want x tilde, how would you do it? Well, you have to apply basically the inverse of this. So if here you call this d plus dt p, right? Let me do a little bit fast cleaning. So if I call it p, the derivative, So applying n minus 1 times p plus lambda on x tilde gives you s. If you want s, then you have to basically apply the reciprocal of this p plus lambda n minus times on s, and that's what you have here, 1 over p plus lambda. The reciprocal of that is applied n minus 1 times on s, and you get what? X tilde. For instance, as I said, if n is 2, then you only need 1 time. So all you need is then this y1 is going to be the same as x tilde when n is 2. And what is y1 in this case? If y1 is taken from s by applying this basically low-pass filter, then y1 is integral from 0 to t of s of t e to the negative lambda t minus t dt, right? And this is basically the time response of this guy here. So this is a convolution, as you know. And now if your st is less than phi, okay, if the magnitude of it is less than phi, as we said, then you can say that the magnitude of y1 is, and you can add absolute value here, is less than or equal. You can bring that phi out, and then this exponential and integral of this exponential is going to be basically 1 minus e to the negative lambda t over lambda. And clearly, since this whole exponential is positive, 1 minus exponential is going to be less than 1, so I can say that this is clearly less than or equal phi over lambda, and this is phi over lambda, not phi times lambda. And that is exactly what we have above. Remember that in here, epsilon was phi over lambda. This is phi, just let's make sure. And you can see that over here too. Okay, so the important thing, as if I just want to summarize it, is if you have bounds on this s of t, then you have bounds on the tracking error, as I just showed you. Not only on the tracking error, you can have the bounds on the ith derivative of the tracking error as well, where here this 2 lambda to the I, for instance, in this case, if I want bound on x tilde dot, that is going to be less than what? Less than 2 lambda times epsilon. Epsilon still the same definition, so it's going to be 2 lambda times phi over lambda, so it's going to be less than or equal to phi. Okay, so you can find bounds on the tracking error and all of its derivatives. Good. Now remember I said that if you want your tracking to happen right away and you get perfect tracking error, you need to have the initial condition of the system to be the same as what? The desired value, or in other words, you need to have x tilde at 0 to be what? Equal to 0. Yes? And that makes a tracking error of perfect tracking error right away. But sometimes this x of 0 is not under your control. Only x desired is what you can pick, and so if you cannot set them equal, then x tilde is not going to be equal to 0, and you won't get a perfect tracking error right away, but you can reach it after some time. How much time? You can mathematically show that the time is going to be n minus 1 over lambda. Okay, where lambda is this constant that you use in the definition of S, and n again is the order of the system. For instance, for a second order system, it's just going to be 1 over lambda. So in the time of 1 over lambda, your x tilde is going to go to 0. Okay? Now, let's go to the big question, the million-dollar question. What kind of U? Remember, the goal is what? The goal is to make this surface S to be an attractive surface, so your trajectories will get attracted to it and then slide on it. Okay, so the question is, how would you pick this control signal U such that this surface S that you pick based on criteria 3, based on definition 3, is an attractive surface? Okay, and your trajectories would get attracted to it and will stay on the surface and slide on it. That's the big question. How would you pick that? Let's go ahead and see that. So the answer is this. We pick u such that condition 5 is satisfied. What is condition 5? Condition 5 says the time derivative of the square of the distance from the surface should be less than or equal negative eta times max times basically the value of s, absolute value, where eta is a positive number. What does that mean? Well, since magnitude of s is positive and eta is positive, then clearly this thing, this right-hand side, is a negative number. And since this time derivative is less than that, then that's clearly negative, okay? So clearly this 1/2 d over dt of s squared is going to be negative. What does that mean? That means the s squared value should go down. It's going to go down, right? Because the derivative of it is and this entity itself is positive, right? So we pick this function s squared basically like a Lyapunov function. If you remember from my previous videos, the function itself is positive, but the rate of change of it is negative. So that means this guy is going to keep going down until what? Until s goes to 0. And when s is 0, that means you are on the surface. So if we can pick u such that this stability condition is satisfied and your distance to the surface goes to 0, and remember the distance to the surface is an indication of your basically your error, then that means the error is going to 0, correct? So eta is basically the rate of converging from out of the surface on the surface. And you see here we are making this squared, not just s, and the reason is s, as I said, could be positive or could be negative. So to make sure that this distance from the surface, this s, is basically going to 0, we have to square it, so either side doesn't matter really. And then this distance is reduced, as you can see, right? Look here, as I'm going toward the surface, this distance s, which here I'm showing by these vertical lines, is getting smaller and smaller until it goes to 0. Now I'm on the surface and it's going to slide down the surface. So this condition 5 is called the sliding condition, okay? The surface S, as I said, we're calling it sliding surface. The way that you pick U so that this condition 5 is satisfied, this control method is called sliding mode control. And since S, when you reach S, you're going to stay on S and you would never leave it, S is called an invariant set, right? Basically, it's kind of like a stable limit cycle. If you watch my video on limit cycle, this is basically like an attraction, right? This is like a black hole. Once it attracts you, you cannot leave it anymore, as long as you can pick U such that condition 5 or sliding condition is satisfied. So far, I have not really answered the question, how would you pick U? But I provided a condition that if this condition is satisfied in terms of S, then guess what? The convergence is guaranteed. Okay, so how do we do that? And this is another view that shows you this relation 5 and the fact that anywhere you start off this surface S, which in this case is a line, then you will get attracted to it. Good. And if you are not starting on it, then in a finite time you are going to reach to the surface. How much is it? I just showed you it's n-1 over lambda. And there is proof for that. If you want, you can watch my reference, which is Slotin and Lee, Applied Nonlinear Control. That is, as I said, one of the best books out there on nonlinear control. If you watch it, basically, there is proof for this bounded error theorem, okay? It is relation 4. Also for this one, there is proof for each and every one of them, but my goal here is not to do a ton of proofs for you. Good. So to summarize, first we need to pick a definition for surface S. Now the definition for S is rather clear. The only thing you can pick is this lambda. The rest of it is directly given. The derivative operator is obvious. The order of the system is obvious. X tilde is obvious. So the definition of S and setting S equal to 0 is obvious. The shape of the surface, as I said, the slope of it, for instance, for a line is determined by this lambda. Okay, and you can see that here, that if it's in the 2D space, then the slope of the surface is what is equal to lambda. Okay, so that's the slope that you move on the surface. It doesn't tell you how fast you converge to it. Okay, that is a separate thing, which I'll show you. But lambda is the slope of the surface. So how fast would you converge from off surface to the surface? That is determined by which parameter? That is by this parameter eta. Look, that's the rate of change of s. So if eta is a bigger number, then you converge, your distance to the surface would shrink faster. So it's eta that controls how fast you converge to the zero error surface, not lambda. Just keep that in mind. So once you pick s, then you need to pick a u such that, as I said, s squared is what is a Lyapunov function of the closed loop surface, or basically that means equation 5 is satisfied. Okay, so let me just add it here. That means equation 5 is satisfied. Good. So let's see how we should pick u by looking at an example. So the way we do it is this. We say, look, I want to stay on S. I don't want to stay away from S. I want to be attracted to S and not move from S. So ideally, I want S to stay at a constant number, ideally 0, perfect. If S is not to change, then one condition I can say is S dot should be equal to what? 0. Now this S dot equals 0 happens when you are on the surface. So when S is 0, when you reach the surface, then you want S dot to stay 0 so you never get off the surface. If this S dot is 0 right off the bat when you start, then of course you only move on a line parallel to what? Parallel to the sliding surface, because S dot 0 means S is constant. But not in the beginning, once you converged. Okay, so look here, let me show you over here. In this area, when I have not converged, S dot has to be negative. I should shrink the distance, okay? And then once I reach here, now S dot has to be 0 so I can stay on it. Good, and I don't get off again. And based on that, we can basically pick u. Really? Yes, I'll show you with an example. This method is called the Flipoff construction method, okay? So let me show you with an example. Let's say the example is, and this is not just a specific example, this is like a general category of second order differential equations. X double dot equals f plus u. Let's say this is your system where f is a nonlinear function, u is the input, control input, and x double dot is the highest order derivative for a second order system. And f is a nonlinear function. Okay, good. Let's say for the moment f is perfectly known. In practice, we don't know f all the time perfectly, but let's say for the moment, f is known. If f is known, what would you pick for the s? Well, s is based on definition d over dt plus lambda to n minus 1. N is 2, so it's going to be to the 1 times x tilde, so it's going to be x tilde dot plus lambda x tilde, right? That combined tracking error. If that's the case, then remember, we need to satisfy this equation, s dot equals 0. So take a time derivative from s. You get s dot to be equal to what? To x tilde double dot plus lambda x tilde dot. Good? Now, what is x tilde dot itself, double dot itself? Remember, x tilde itself is x minus what? X desired, correct? That's the definition. So if I add double dot, what is it? What is it going to be? It's going to be basically x double dot minus x desired double dot, right? Like this. So that's what I replaced it right here. And this lambda x tilde dot is just added. Good. So now what is this x double dot, right? What is this? Based on the equation of motion for the system, x double dot is what? Is f plus u. So I'm going to replace it right down here. That's what you see. And the rest of it I just write. Now, since this S dot has to be equal to 0, from here I solve for u. So I take every term to the other side, so u becomes what? Negative f plus xt double dot plus what? Minus lambda x tilde dot. If I pick u like that, then I have guaranteed convergence, and you can check it. If you just combine 7 and 8, if you plug 8 into 7, what would you get? You get x double dot equals, if f is known, then this f and that f, this positive and negative f, would cancel each other. So you simply get xt double dot minus lambda x tilde dot. And if you take everything to one side, then you get x tilde dot plus lambda x tilde double dot plus lambda x tilde dot, which is the same as s dot, and that is equal to what? 0, which means s is going to stay constant, and if you are on the surface, that means you're going to stay on it forever. So you see, this is working perfectly fine if this f that I use in the control signal u is working. Solving it from s dot equals 0 will give me what I need. The problem is what? Okay, that's what I explained. The problem is two things. One, you don't know f exactly. F has uncertainty. Second thing is, when you move toward this surface, let's take a look what happens. Across this surface S, there is discontinuity. What does it mean? It means on one side of it, S is negative, on the other side, S is positive. Well, what's the problem? The problem is this. That if you are on the right side here, right, and s is bigger than 0, then u should be such that it pushes your system back to the left, back toward the surface. If you're on the left side of it, then your u should be such that you are pushed to the right, so again you go back to the surface. So when we say there is discontinuity across s, we are not talking about the s itself. The s is negative, 0, positive. So s is continuous, but the control signal u that you pick is not going to be continuous. On one side is in one direction, on the other side is like negated. So it has this kind of jump. If you, for instance, plot u versus t, right? If you plot this u versus t, you see that in one side, for instance, is positive, on the other side is negative, and so on. So let me just add it here. There is discontinuity. Note that for u, there is discontinuity across what? Across s. So it's basically like you're switching the control, right? On here, you have one kind of control. When you reached here, that s of 0, now you have to switch to the other side. So this behavior is very similar to a thermostat, right? In a thermostat, if this is the set temperature, and this is T, if this is your set temperature, what would you do? So this is like temperature desired. You turn on the furnace and it keeps going up, but when it reaches here, right? So here is when the thermostat is on, here when it's off, the furnace. When it reaches here, the switching does not happen right away. I mean, when you command the furnace to go off, it has a little bit transport lag, right? So the time that you command the furnace to be on and the time it actually turns on, or the other way, when it turns off and the time you command it to turn off, there will be a little bit transport lag, because nothing will be immediate and instantaneous. So the system will be a little bit hotter than what it should be. When you turn it off, again, it starts going down, but before it goes back on, it probably loses a little bit heat temperature, and it keeps going, and you get basically this dead zone area and this phenomenon called chattering. Okay, so there is some time that needs for the switching to happen. So if you use the sliding mode control, you're going to see that your trajectory is going to go to either side of your surface, and it keeps going back and forth, and there will be a bunch of crossings, which we call chattering. And in general, this chattering is not a good thing for several reasons that we're going to see. One of them is it makes the control effort a lot higher. And if you don't know what control effort is, please watch my video on the LQR control in optimal control. And you see that basically it's proportional to something like integral of u squared dt. Okay? And that makes that one bigger. Also, since it adds some vibrations to the system, if it's a mechanical system, it can create vibrations in the system. And if there are unmodeled dynamics in the system with natural frequencies similar to this chattering frequency, then you can excite those modes of frequency and you can cause some big resonance. So in general, this chattering is not something good and we have to think about it. But for now, we want to see how to implement this sliding mode control for one actual physical system, because here it was too general of an example. So I'm going to show you a more tangible example and see how to design the surface and how to apply the sliding condition by picking an appropriate u, see the chattering in it, and then coming up with a solution how to basically get rid of the chattering. Okay? So let's go ahead and see what we can do. So before I go to the actual physical system, remember I said we have two problems. One is the chattering, which we'll deal with it at the end of this video. The second problem is this controller that I picked, this u that I picked, was based on the assumption that that I know the f perfectly. So this law 8 is only good when I know f perfectly. If I don't know f and all I know is just f hat, an approximate of f, can I still use this rule number 8? Would that basically give me any performance that I need? So let's take a look here. So let's say we don't know f and all we know is just what? We just have f hat. But as I said, we have some bounds on the uncertainty. For instance, the difference between what we know from f and the actual f, the absolute value of that is less than or equal some capital F. Clearly, this capital F is a function, okay? It's not a constant. This is a function of, it could be x, x dot, or in general, vector x. Good? So if the distance between our estimate of the function and the actual function is less than or equal some f, then the controller that we pick is exactly like 8, except f is replaced by f hat. Good? And as I said, since we have to account for this discontinuity of u on the two sides of s negative and s positive, what we do is this signal that we pick, the u, is this u hat that we had in 10 minus what? K sine of s. Now clearly you can see that if sine of s is, if s is positive, sine of s becomes 1, so your u becomes what? Becomes u hat minus k. And if s is negative, then your u becomes what? U hat plus k. You see that? So now I have this discontinuity here. So if this average here, this average signal is like u hat, then this is what? This is like plus and minus k. Okay? So clearly I have this continuity now. The question is, how would you pick this k? How would we pick this k such that we assure this sliding condition is satisfied? Can we pick just any k? The answer is no. This k needs to have some condition for the sliding condition to be satisfied. What is it? So let's find out. By the way, k in general does not need to be constant. It could be some function of the vector x. Now, how do we pick it? So here I can show you that if we pick k to be equal to f plus eta, f is, remember, is the upper bound on the distance between your estimated function and actual function, and eta is this rate of shrinking in the distance squared that I need in equation 5. Okay, so let's take a look. If I pick k based on 12, do I have condition 5 satisfied? Let's find out. So the left-hand side of that was 1/2 d over dt of s squared, which is going to be s dot. Now we'll keep s as is, but for s dot, what is s dot? If we go back and look at what s dot was here, take a look. This is s dot, and the thing we found for s dot was this. F plus u minus x double dot plus lambda x tilde dot, right? So I'm going to replace it right here. That is s dot. Now, the u that we pick is what is u hat minus k sine of s based on relation 11. And then for u hat, we're going to pick the signal we have in 10. So now that is going to come right down here. And so negative u hat or positive u hat that you have is negative f hat plus xt double dot minus what? Lambda x tilde dot. Okay, so that is u hat here. And this minus k sign makes it u. So now if you look, this term and this term would cancel. This term and this term would cancel. And so your ss dot, or the left-hand side, is going to be equal to the remaining of it, which is f minus f hat minus k sine of s, the whole thing times s. Now we multiply it by s, so you get f minus f hat times s minus k times s sine of s, which you can write it as absolute value of s. Good? Yeah? Now, for k, I'm going to replace what I picked in 12. I write it as f plus eta. That is that k. Now, what is this here? Remember the relation that f hat minus f was less than or equal capital F. So if I expand this, let me just expand it. If I expand this, this is going to be f minus f hat, the whole thing, minus f times s, and then minus eta times absolute value of s. True? Now, what is this entity here? Based on relation 9, clearly this entity has to be negative because the magnitude of the first one is less than the second one. So clearly that whole entity is going to be less than or equal this, which you can see over here. And this is, if you remember, this 13 is now exactly equation 5, the inequality 5 that we needed. Remember? Yes? So it's satisfied. So to control system 7, if I want to summarize, in order to control system 7, what do I need to do? First, we pick what? In order to control system 7, we pick u based on relation 11, where the u hat in relation 11 is coming from relation 10. So that's the control signal that I pick. And also the k that I need in 11 is coming from 12. Okay, so if I pick 10, 11, and 12, if I pick 10, 11, and 12, that should exactly give me what the controller I need in order to guarantee my sliding condition and guarantee my convergence of error to 0. If I want to control system 7 with such dynamics. And this is the surface that I picked. This is the sliding surface. Good? So I guess we looked at all of that. Now you might say not always the coefficient of this u in this system is 1. Sometimes it's b, or it could be the coefficient of x double dot to be b, right? Like for instance a mass times acceleration. So if one of these u or b has a constant behind it, can I still use the same control law? Well, yeah, well, with a little bit modification, yes. So for instance, if I have a system like this, what would you do? You divide both sides by m, you get 1 over m and 1 over m times f. So this 1 over m times f, you can call it your new f, and this 1 over m, you can call it a constant like b. So your equation will be x double dot equals some new f plus b times u, and this is exactly what I have over here in relation 14. So if your u has this gain, how would you modify the relations that you had? Remember 10, 11, 12, so you still can apply it. Still, let's say the distance between f hat and f is less than or equal capital F, so this is the upper bound on your uncertainty on the function. And this b here, also let's say that one is uncertain and it's between a b min and a b max. Here you define two parameters. One is b hat, the other one is beta. B hat is the geometric mean of b min and b max. And beta is the square root of b max over b min. You can show that here your control signal u is the same as 10, it's still u hat minus k sine of s. Look at it, 11, sorry, u hat minus k sine of s, but pre-multiplied by b hat inverse. Okay? So very similar, except there is this b hat inverse, and b hat here is the geometric mean of the b min and b max. And what would you pick for k? Is k still f plus eta? No, this time k is a little bit more complicated. The thing that you pick for k is bigger than or equal, so the minimum of it is when it's equal, beta times what? F plus eta. Remember last time it was just this inner parenthesis term. Now you have to multiply it by beta, which is the square root of b max over b min, plus beta minus 1 times the magnitude of u hat. Okay, now for the physical example, let's look at an unmanned underwater vehicle, like a submarine or anything submersible, or you can also look at it as an object in free falling with air drag. So the only forces on the object are drag force and gravity. And the equation of motion is my double dot plus the drag force equals the external force. Here, let's say if it's a submarine, this is the upward force from the props, and c is the drag coefficient, right? So if you take everything to the other side and divide by m, you get this equation, which now exactly matches the format of 14, x double dot equals f plus bu. Instead of x, we use y because this is vertical motion, but it doesn't really matter. So you can see that the b parameter here is 1 over m, and the f function is basically negative c over m times y dot times magnitude y dot. Okay, now since n is 2, our surface S is going to be y tilde dot plus lambda y tilde. The control rule based on 15 is what we have just up there. U is b hat inverse times u minus k times sine of s, where s is we just defined. So what we need is to define is u hat and k and then b hat inverse. Okay, so u hat is given up here. We have u hat, that's negative f hat plus xt double dot minus lambda x tilde dot, for which we have f hat already. Okay, so that we have, that's what you can see here. This is your u hat, so f hat of it is already determined. Yd double dot is under our control. Y tilde also, lambda we pick. S is also taken care of. So what we need, as I said, is b hat. B hat, we already have it. So b hat inverse is 1 over that, the square root 0.5. And then k is bigger than or equal this number. So here we use the lower limit. So we pick it equal to beta times f plus eta plus beta minus 1 times this magnitude of u hat, where here you have to pick again a an eta parameter. Beta of it is already determined, so we need to pick eta, and f is already determined as well. So what we really need to pick is this parameter eta, which is the speed of convergence back to the surface, as well as lambda, which determines the slope of the sliding surface. Once we have those, then our control is ready to be deployed. So let's go ahead and look at the MATLAB Simulink demo that I made for you. Okay, so this is the Simulink model. This is the model of the underwater vehicle. And you can see this is 1 over m, where m is basically, in this case, picked as 1. So any number between 1 and 2 we can pick for m. Here I just chose 1, but if you want, you can change it to 1.5. And then c over m, here I chose c of 0.5, and again m of 1. So c over m is negative with negative sign, negative 0.5. Initial velocity is 0. Initial position is 11 meters. Now here I made them not equal to each other. Initially I tried it for those two being equal to each other, but now I changed it. So if you want, you can make the remember that condition 2, you can make the initial condition on x and x desired to be the same, or you can make them different. But since I want you to see that if you don't start on the surface, how you would go to it, I made the two conditions a little bit different. So what is the desired thing here? If we see, the desired is a drop from 10 meters at the slope of 1. So after 10 seconds, you should go to elevation 0, right? And here it is measured from the bottom of wherever it is, not from the top of it. Otherwise, this has to start at 0 and go negative. So my reference for y is at the bottom of that, whatever it is, lake, ocean, whatever. And so it's 10 minus t, and then the y dot desired is -1, derivative of that, and y dot yd double dot is 0, of course. I pass all of those desires and derivatives as well as y and y dot of the system to my controller. Here, beta, remember, was a square root 2, f was 0.2, y dot absolute value y dots. For eta, I pick 10, and for lambda, I can pick 10 or a different number. Here, I changed it to 3, but feel free to change these numbers. This eta here, also, I changed it to 2 again, so you can feel free to change them. Initially, I ran it with 10 and 10, but now I'm changing it to what? To 3 and 2. As I said, these are the parameters under your control, and you can change them here. So let's say we go with what I have right now. And if you run this, you are going to get y and y desired that you can compare side by side, or subtract and get y tilde, or the error, which is y minus y desired. And here is the plot of the error. Okay, this is the error plot. If you look here, see the error is oscillating around 0 and never really being damped out. Okay, if you zoom in, you can clearly see it becomes positive and negative here. Or if you look at y versus y desired, also you can see that y goes above and below y desired, right? So you can see that if you zoom in some area. Let me see if I can zoom a little bit further for you so you can see better. Maybe here. There we go. Look, you see right now y, the blue curve, is below y desired, but then it goes above it. And as we move on, look here, above, and then it should go below. There we go. You see it goes below and again goes above, and this up and down thing happening. But if you really want to see chattering, I added for you this trajectory, y dot versus y, so we can see the actual chattering here. So if you click here, this is where you can see the actual chattering. System starting from initial condition y of 11, y dot of 0, and then moving on to y of 0. Okay, and y dot of -1. Look here. So you start from here and move on, and there we go. Look here you can very well see the chattering. Okay, so chattering is well observed here. And as I said, this is my controller. Everything is shown here. The last thing I need to talk about for you is how to get rid of the chattering. Because as I said, chattering can increase the control effort and excite the unmodeled dynamics or frequencies of the system. So we need to smoothen this chattering or this control switching. And one of the ways that they do it, I guess it is inspired by fluid mechanics or something, they define a boundary layer around the desired surface S of 0, and inside this boundary layer they smoothen the control law because all of the chattering happens around this S of 0. So if your boundary layer is thick enough, then you can literally damp out all of those chatterings. Okay, here there are two parameters. One is phi, which we call the boundary layer thickness, and the other one is epsilon, which is called the boundary layer width. Okay, so those are like the basically intersections of this boundary layer with x and y axis. It's like half of them basically. So you can parameterize your boundary layer by epsilon and phi. So the way you define phi is to say that boundary layer is all of the points in the state space where S is less than phi. Okay, so you can see that is a picture of boundary layer here. And inside this boundary layer, one simple way to do it is if you want this U to not be basically oscillating up and down versus S, okay, and jumping from positive to negative and so on, one way you can do it is inside the boundary layer, you can basically connect them with a simple line. Okay, and the way you can do it is by dividing S by phi. Okay, so when S is basically less than positive phi, bigger than negative phi, this ratio becomes positive 1, negative 1, between negative 1 and positive 1, and then you apply a saturation block on it. And saturation gives an output of 1 as long as you are between the two saturations, and negative 1 if you are on the other side, and then it keeps it at 1 and negative 1 if you move outside the boundary layer. So if you want, instead of using this U hat minus K sine of S, you can basically use what? U hat minus K saturation of S over phi, where again phi is the thickness of the boundary layer. Now the way this picture is shown, although I got it from the textbook, but I think to me this makes more sense if this is phi, not the other one is. And so a simple saturation function, as you can see here, will do the job. So linear inside the boundary layer, outside of it as fixed. And this can replace all of this basically oscillations back and forth for you. That makes it a lot nicer. So this is my control. Here I provided a switch for you, and if the switch is up, you're going to use negative K sine of S. So you're going to go with chattering, right? But on the bottom, I divided S by phi, and here for phi I used 2. So 1 over phi is 0.5, so this is S over phi, and then I passed it to the saturation block, and for limits I use 1 and negative 1. So if you double click and the switch and bring it down, now you're going to use this basically a smoothened version of your control signal. So if you pass that, for you now you should not really see much of chattering as bad as last time. So here, let's go ahead and run it again with this smoothened version. And if you look at y tilde this time, you can see that all of those ups and downs are gone, and you see basically this smooth curve. One thing I have to mention is, because here inside the boundary layer you are using an approximation to the actual U, you will not get perfect tracking error, but the good thing is you are protected against unmodeled dynamics and you basically get robustness. Okay, so if you look here at the very end, you see that the tilde is not exactly 0, right? You see it's about like negative 0.01 or something. Okay, it's not perfectly 0, but if that's acceptable for you, that should be good enough for a good robust and good performance. And if it's not, you can change the size of the boundary layer. Okay, and here also you can see the Y and YD, and this time you should not see the up and down motion. You see Y stays on one side of YD, and it's good to take a look at this one as well. See if the chattering is improved or gone altogether. And guess what? As expected, it is all gone together. Remember what it was last time? It's all this chatter. Now it's not there anymore. Beautiful, huh? So you can clearly see that it is actually doing its job. Okay, so I have added all these options for you, and I'm gonna give you this file so you can practice with it and learn from it. Again, feel free to change eta, feel free to change lambda. The one that really matters is eta. Remember, eta is the one that controls the speed of convergence to the surface. And as I said, with this switch, you can see the chattering versus not chattering, okay, and smoothened version of the control law. And if you want also, you can bring in another one of these and you can plot U versus S, because here you have U, and one place here you should have S. There we go. Look here, it's right there. So if you want, you can also send out S, and you can plot S versus U, right? So you can just grab another one of these, and let's say I want to plot U, and so U versus S, and I want to plot, let's say, S here. Okay, so you can do any plot that you want, and you can look at the behavior when you have this switch, or if you don't have the switch, you can look at U versus S. And actually I said to myself, let me show it to them before I finish the video. So here is U versus S plot, and if you look at this area here, you clearly can see that basically around S of 0, you have what? You have a bunch of oscillations here. Okay, there we go. Right, so you clearly see that it does not look very smooth, while if you switch to the other behavior and run it, it should be a lot nicer behaving. And here is the plot of that. Okay, so hopefully the video was useful to you. You learn about this complicated topic, sliding mode control, which is for nonlinear systems in general, although you can apply to linear systems as well, but this is typically used for nonlinear systems when you want to do a robust control. You don't know something about the system, or you neglected it, or you simplified it, and you want a good tracking. At the same time, you want to make sure you can reject all of those disturbances and have a robust control. Thank you so much for your attention. I'll see you in the next video.